Well, you know what time it is. It's your favorite time of the day when somebody you don't know with a melodious voice is going to give you the answer to one of these nebulous looking LeetCode problems, in this case coin change, a classic dynamic programming question. So what does that even mean? Well, let's look at the question first. It says you're given coins of different denominations and a total amount of money amount. Write a function to compute the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So let's look at the first example. You're given coins 1, 2, and 5 and the amount 11. You say the minimum amount of coins you need is 3 because you could make up 11 with 5 plus 5 plus 1. So 2 5s and 1 1. Now you have coins. You only have one coin, which is 2. The amount is 3. Can you make up the 3 amount? And the answer is no. Now you have coins 1. Can you make up the amount? The fewest number of coins that you could use is 0, actually. So you have coins, but you don't need to make any amount, actually, so you don't need to use any of your coins. If you have the amount 1 and you have the coins, and you have a coin that has a value of 1, well, you could use that coin, and that means your minimum is 1, and so on and so forth. So here you have an amount 2, you have coins of type 1. Your output is 2 because 1 plus 1 equals 2. So you want to find the minimum amount of coins. So whenever I'm asked a min or a max type of problem, I always do my own little function just to get into the groove. I do my own min or max function, and let's do that right now. So it takes in two integers by reference, two integers a and b. So we say if a smaller than b, return a, else return b, and it's that simple for that. Now we know we have our base case, which we saw right over here. If the amount is 0, we always return 0, no matter what kind of coins you have. You won't be able to use them. So if amount equals 0, return 0. Okay, done with that. Next, we might want to sort the coins, and we have an algorithm for that. So let's just sort them over here. Oh, sorry, from begin to coins.end. Okay. Next, we would like to come up with a dynamic array. So this takes memory from the heap, and how do we do this? We set it to, we'll call it DP for dynamic programming, equals new int, it's an integer array of size amount plus 1, because at some point we're going to want to refer to this actual amount, and since this is a 0-based array, since this is a 0-based array, well, we could refer specifically to that amount later and not amount plus 1. It starts off at 0, not at 1. And then, well, how could we do this? One way that we could do this is populate each of the elements of that new array by I smaller than amount plus 1. We could populate each element of the array by amount plus 1. And the idea is that no matter what, well, this will act as our infinity, because our coins cannot be less than 1, and I guess that's over here. The coins cannot be less than 1. So that means that even if you added up all the ones, which would be the maximum amount of coins, the most you could get is amount. If you get amount plus 1, that means you never use the coin. Now, okay, you know what? Let's, instead of having it with a dynamic array, let's blank that out over here. Let's take advantage of the standard library. Let's make this a vector, which instead of these 3 lines, we could do it all in 1 line. Let's call this vector dp, and we can make it of, we could initialize it at size amount plus 1, and we could initialize every value to amount plus 1. And I believe that's how we do that. Let's check that. Let's just run the code. Okay, yeah, that actually works. So it's just telling us that it didn't return anything, which is something here. In fact, let's return something. This is just so that we could satisfy the function. We'll clear that up later. And notice that with this vector dp, we don't need to do any delete function. We don't need to worry about the memory. We could have also used a unique pointer to solve the same kind of thing. Okay. Now we're going to want to set the first element to 0. That's the only one we set to 0. The others are, again, immediately by default set up as amount plus 1. So if we just display dp 1, for example, let's just see what it gives us. We see that we were given 11 and we're shooting at 12, and that's all because of our automatic initialization that was done in 1 line instead of 2. So let's get rid of that over there. Okay, next we're going to want to iterate through all the coins. So through all the amounts before amount, because that's what dynamic programming is. You start with the simplest case, in this case 0, then we'll look at 1, all the way up until the value of amount, and see what we could do with the coins that we have available for that particular amount. So we're going to iterate I to amount plus 1, I plus plus. Now we want to go through each coin and see whether we could use those coins for example, the value of 0 or 1 or 2, all the way up until amount. So our base case is this 11, just like they gave us on that original example. We should find 3 at the end. So we're going to iterate through the coins, and we're going to say if the coin that we're currently looking at is smaller or equal to I, which is the current amount we're looking at, that means the amount at that particular position, so the least amount is my min with the current amount that it was at now, which in this case is amount plus 1, which is its current amount, or 1 plus dp, I minus c. Okay, so what's actually happening here? When it's looking at the particular positions, say we're looking at amount 3, and we have coins 1 and 2 over here. Well, if we're looking at amount 3, we would have already seen amount 0 and amount 1 and amount 2. If we're just looking for coin 1, we know that coin 1 to do 0 would have needed 0 coins. Coin 1 would have needed 2 coins here. Coins 2, we see that 2 is the coin that we're looking at, 1, is smaller than 2. So we're saying this value at 2, the number of coins that we need to use, is 1 plus my 2 minus 1, which is 1. So that's the value here. So that's why we're going to get 2. And here we're going to do the same thing. 3 minus plus the value at over here, which is 3 over here. Now, remember, we want the smallest amount used. So if we get to, for example, eventually 4 and 5 over here, and at this point with the ones we would have used up 5 coins, well, later if we're looking at coin 5, we wouldn't have been able to fill up any of these squares over here. Why? Because 5 is 5 in this case would not have been smaller or less than I, or equal to I. Once it is, we take this 1 plus the value at 0, which is 0, and we make it 1. And that 1 is actually smaller than the current 5, which we got from the 1. And that's why it's going to override it at that point. Well, I hope you got that. Okay, so now at this point, if at the end of all this, if your value at dp amount is smaller than amount plus 1, so meaning something hits at that particular amount, if coins were able to be used, then let's just, we don't need the brackets here, return dp amount, else return -1. That means we couldn't use anything. So there you have it. We just need to return something. It's actually never going to hit this thing over here, but the compiler might give some sort of warning, meaning that you need to return something if it's asking you to return something, which it is over here. Let's see what happens when we run this. Use of undeclared identifier mymin. That's line 33. dp equals mymin. Oh, sorry, I called that mymax. That should be mymin. Okay, so here we see that that worked. And here we see that that worked too. Let's run that again. It would be interesting to compare what happens when we do the dynamic array or even some sort of unique pointer like situation instead of this vector. Well, that's all for now. Thanks again. Have fun.